In this lecture, we'll be delving into the fascinating world of discrete time Markov chains. We've previously discussed that independent and identically distributed, or IID, sequences are the simplest forms of discrete time random processes. However, a limitation of IID sequences is that they don't effectively capture correlations within the data. So let's define what a Markov process is. A stochastic process, which will denote as X mapping from omega to script X superscript T with a state space script X and an ordered index set T, is defined as Markov if conditioned on its present state xt, its future represented by sigma of xu for u greater than t is independent of its past represented by sigma of xs for s less than t. We'll use the notation script f subscript t to represent the history of the process up until time t. This is defined as sigma of xs for s less than or equal to t, that is for any Borel measurable set B, an element of script B of script x, for any ordered index set T containing any two indices u greater than t, we have the probability of the set u is in B given script f subscript t equals the probability of the set u is in B given sigma of xt.
Next, let's rewrite the Markov property more explicitly for a process X that maps from omega to R superscript R. For all X and Y belonging to the state space script X, a finite set S, which is a subset of R, such that the maximum of S is less than T, which in turn is less than U, and H subscript S of X subscript S, defined as the intersection over S in S of the set XS less than or equal to XS, which is an element of script F subscript T. We have the probability of the set XU less than or equal to Y given H subscript S of X subscript S intersected with the set XT less than or equal to X equals the probability of the set XU less than or equal to Y given the set XT less than or equal to X.
Now let's move on to discrete time Markov chains. For a state space script X, which is a subset of R, and a random sequence X mapping from omega to script X superscript Z plus, we define the history until time in an element of Z plus as script F subscript N, which is equal to sigma of X1 through Xn. Recall that the event space script F subscript N is generated by the historical events A subscript X of X, defined as the intersection from I equals 0 to N of the set Xi less than or equal to Xi, where X is an element of R to the power of N plus 1. When the state space script X is countable, the event space script F subscript N is generated by the historical events H subscript N of X, defined as the intersection from I equals 0 to N of the set Xe equals Xe, where X is an element of script X to the power of N plus 1. That is, script F subscript N is equal to sigma of H subscript N of X for X in script X to the power of N plus 1.
Now let's formally define a discrete time Markov chain or DTMC for a countable set script X a discrete valued random sequence x mapping from omega to script x superscript z plus is called a discrete time Markov chain if for all positive integers n in z plus, all states x and y in script x, and any historical event h subscript n minus 1, which is the intersection from m equals 0 to n minus 1 of the set xm equals xm, an element of script f subscript n for x not through xn1 in script x to the power of n, the process x satisfies the Markov property, the probability of the set xn plus 1 equals y, given h subscript n minus 1, intersected with the set xn equals x, is equal to the probability of the set xn plus 1 equals y, given the set xn equals x base.
The above definition is equivalent to saying that the probability of the set xn plus 1 less than or equal to x given script f subscript n equals the probability of the set xn plus 1 less than or equal to x given sigma of xn for a discrete time, discrete state space Markov chain x. This is because script f subscript n equals sigma of h subscript n of x for x in script x to the power of n, and sigma of xn equals sigma of the set xn equals x for x in script x. Let's consider an example, a random walk. A random walk S mapping from omega to script x superscript n with an independent step size sequence x mapping from omega to script x superscript n is Markov for a countable state space script x that is closed under addition. Given a historical event h subscript n minus 1 of s defined as the intersection from k equals 1 to n minus 1 of the set sk equals sk and the current state, the set Sn equals Sn. We can write the conditional probability. The probability of the set Sn plus 1 equals Sn plus 1 given h subscript n minus 1 of s intersected with the set Sn equals nn is equal to the probability of the set xn plus 1 equals Sn plus 1 minus n given h subscript n minus 1 of s intersected with the set Sn equals Sn. This in turn is equal to the probability of the set Sn plus 1 equals Sn plus 1 given the set Sn equals Sn, which simplifies to the probability of the set xn plus 1 equals Sn plus 1 minus Sn. The equality in the second line follows from the independence of the step size sequence. In particular, this stems from the independence of xn plus 1 from the collection sigma of S0 x1 through xn, which is equal to sigma of S0 S1 through Sn. Next, we introduce the concept of the transition probability matrix. We denote the set of all probability mass functions over a countable state space script x by script m of script x, which is defined as the set of nu, an element of 0 to 1 to the power of script x, such that the sum over x in script x of nu subscript x equals 1. The transition probability matrix at time n is denoted by P of n, an element of 0 to 1 to the power of script x times script x such that its xyth entry is denoted by pxy of n, which is defined as the probability of the set xn plus 1 equals y given the set xn equals x. This is the transition probability of a discrete time Markov chain x from a state x in script x at time n to state y in script x at time n plus 1. We observe that each row p subscript x of n defined as p xy of n for y in script x, which is an element of script m of script x, is the conditional distribution of xn plus 1 given the event that xn equals x. Let's define some matrix properties. A matrix A, an element of R plus to the power of script x times script x with non-negative entries is called substochastic if the row sum, that is the sum over y in script x of a xy, is less than or equal to 1 for all rows x in script x. If the above property holds with equality for all rows, then it is called a stochastic matrix. If matrices A and A transpose are both stochastic, then the matrix A is called doubly stochastic. We can make the following observations for stochastic matrices. First, every probability transition matrix P of n is a stochastic matrix. Second, all the entries of a substochastic matrix lie in the interval 0 to 1. Third, each row, a subscript x defined as a xy for y in script x of the stochastic matrix A, an element of R plus to the power of script x times script x belongs to script m of script x. Fourth, every finite stochastic matrix has a right eigenvector with a unit eigenvalue. This can be observed by taking U transpose equals the vector of ones of length absolute value of script x. Then we see that A times U equals U, since the xth component of A times U is the sum over y in script x of a xy times ui, which equals the sum over y in script x of a xy, which equals ux for each x in script x. Fifth, every finite doubly stochastic matrix has a left and right eigenvector with a unit eigenvalue. This follows from the fact that finite stochastic matrices A and A transpose have a common right eigenvector u. It follows that A has a left eigenvector u transpose. Sixth, for a probability transition matrix P of n, we have the sum over y in script x of f of y times pxy of n equals the expectation of f of xn plus 1 given the set xn equals x. Now let's discuss homogeneous Markov chains. In general, not much can be said about Markov chains with index dependent transition probabilities. We will consider the simpler case where the transition probabilities pxy of n equal pxy and are independent of the index n. A discrete time Markov chain with a probability transition matrix P of n that is independent of the index is called time homogeneous. We call the linear operator P with entries pxy for x, y in script x, the transition matrix. Consider an example, an integer random walk. For a one-dimensional integer valued random walk S, mapping from omega to z superscript n with an IID unit step size sequence X, mapping from omega to the set -1, 1 superscript n, such that the probability of the set x1 equals 1 is P, the transition operator P, an element of 0 to 1 to the power of z times z is given by the entries pxy equals p times the indicator that y equals x plus 1 minus p times the indicator that y equals x minus 1 for all x, y in z. Another example is a sequence of experiments. Consider a random sequence of experiment outcomes x mapping from omega to the set 0, 1 superscript z plus, such that the probability of the set xn plus 1 equals 0 given the set xn equals 0 is 1 minus q, and the probability of the set xn plus 1 equals 1 given the set xn equals 1 is 1 minus p for all n in z plus. Then we can write the probability transition matrix as P equals the matrix with rows 1 minus Q, Q and P, 1 minus P. Consider a time homogeneous Markov chain X mapping from omega to script X superscript Z plus with a countable state space script X and transition matrix P. We will respectively denote the conditional probability of events and conditional expectation of random variables conditioned on the initial state, the set x naught equals x by p subscript x of a, defined as the probability of a given the set x naught equals x, and expectation subscript x of y defined as the expectation of y given the set x naught equals x. A proposition states that condition on the initial state, any finite dimensional distribution of a homogeneous Markov chain is stationary. That is, for any finite n m in z plus and states not through xn in script x, we have the probability of the intersection from I equals 1 to n of the set z equals c given the set x naught equals x naught a is equal to the probability of the intersection from I equals 1 to n of the set xm plus I equals xe given the set xm equals x naught, which is equal to the product from I equals 1 to n of p subscript xi 1 xi. Let's look at the proof. Consider a homogeneous Markov chain x mapping from omega to script x superscript z plus with a natural filtration script f bullet such that script f subscript n is defined as sigma of x naught through xn for each n in n. Using the property of conditional probabilities and the Markov property of x, we can write the conditional probability of the sample path x1 through xn given the event that x naught equals x naught as the probability of the intersection from I equals 1 to n of the set xe equals xi given the set x naught equals x naught, which is equal to the product from I equals 1 to n of the probability of the set xe equals xe given the intersection from j equals 0 to I minus 1 of the set xj equals xj. This simplifies to the product from I equals 1 to n of the probability of the set c equals xe given the set xe1 equals xi1. Continuing the proof using the property of conditional probabilities and the Markov property of X, we can write the conditional probability of the sample path xm plus 1 through xm plus n given the event that xm equals x naught as the probability of the intersection from I equals 1 to n of the set xm plus I equals xi given the set xm equals x naught. This is equal to the product from A equals 1 to n of the probability of the set xm plus I equals xc given the set xm plus I minus 1 equals xc minus 1. From the time homogeneity of transition probabilities of the Markov chain X, it follows that both these transition probabilities are identical and equal to the product from I equals 1 to n of P subscript xi minus 1 xc. As a corollary, the n-step transition probabilities are stationary for any homogeneous Markov chain, that is for any states x naught, x sign in script, x and n, m in n. We have the probability of the set xn plus m equals xn given the set xm equals x naught is equal to the probability of the set xn equals xn given the set x naught equals x naught. The proof follows from summing over all possible paths x naught through xn and xm through xm plus n. In particular, we can partition the events, the set xn equals xn and the set xm plus n equals xn in terms of unions over disjoint paths. The set xn equals xn is the union over x in script x to the power of n minus 1 of the intersection from I equals 1 to n of the set c equals xc. Similarly, the set xm plus n equals xn is the union over x in script x to the power of n minus 1 of the intersection from I equals 1 to n of the set x m plus I equals xci. The result follows from the countable additivity of conditional probability for disjoint events of taking distinct paths and the fact that the probability of taking the same path is identical for both sums.
Next, let's discuss the transition graph. A time homogeneous Markov chain X mapping from omega to script X superscript n with a probability transition matrix P is sometimes represented by a directed weighted graph G equals script X E dub, where the set of nodes in the graph G is the state space script X. The set of directed edges E is the set of possible one-step transitions indicated by the initial and final state X and Y respectively that are element of the Cartesian product script X times script X such that P xy is greater than 0. In addition, this graph has a weight to E equals Pxy on each edge E from X to Y.
Let's revisit the integer random walk example. The time homogeneous Markov chain for the integer random walk can be represented by an infinite state weighted graph. We have plotted a subgraph of the entire transition graph for states minus 1, 0, and 1 as shown in the figure. P is the probability for a positive step and 1 minus P for a negative step. Now for the sequence of experiments example, the time homogeneous Markov chain can be represented by the following. Two-state weighted transition graph G equals the set of states 0.1 set of edges E with weights W, which is plotted as shown. Let's move on to the random mapping theorem. We've seen some examples of Markov processes where xn equals xn1 plus zn and z mapping from omega to lambda. Superscript n is an IID sequence independent of the initial state x naught. We will show that any discrete time Markov chain is of this form, where the sum is replaced by arbitrary functions. The random mapping theorem states that for any DTMC x mapping from omega to script x, superscript z plus, there exists an IID sequence z in lambda to the n and functions fn mapping from script x times lambda to script x such that xn equals fn of x n1 zn for all n in n. A random mapping representation of a transition matrix P of n on state space script x is a function fn mapping from script x times lambda to script x along with a random variable zn mapping from omega to lambda, satisfying for all x, y in script x, the probability of the set fn of x, zn equals y is equal to p xy of n. For the proof, it suffices to show that every transition matrix P of n has a random mapping representation. Then for the mapping Fn and the IID sequence, Z mapping from omega to lambda to the n, we would have Xn equals Fn of x and 1, Z, n for all n in n. Let lambda be defined as the closed interval 0 through 1 and we choose the IID uniform sequence Z mapping from omega to lambda to the n. Since script x is countable, it can be ordered. We let script x equal n without any loss of generality. We set f sub xy of n defined as the sum over Gill less than or equal to PA of px2 of n and define the function fn mapping from script x times lambda to script x for all pairs x z in script x times lambda by fn of x. Z is defined as the sum over y in n of y times the indicator that f sub x y minus 1 of n is less than z, which is less than or equal to f subscript x y of n. This is also equal to the infimum of the set of y in script x such that z is less than or equal to f sub x y of n. Since fn of x, zn is a discrete random variable taking value y in script x if and only if the uniform random variable zn lies in the interval open from f sub x y minus 1 of n through f sub x y of n closed. That is the event that fn of x zn equals y is the same as the event that zn is in the interval open from f sub x y minus 1 of n through f sub x y of n closed for all y in script x. It follows that the probability of the set fn of x zn equals y is equal to the probability that f sub x y minus 1 of n is less than zn, which is less than or equal to f sub x y of n. this is equal to f sub x y of n minus f sub x y minus 1 of n, which is pxy of n. This concludes the proof and our discussion for this lecture.